Hi everyone, and welcome to this lesson where we're going to look at relative extrema. Please pause the video and read example 1, and then we can work on it together. Suppose that the manufacturer of a diet soft drink is disappointed by sales after airing a new series of 30-second TV commercials. The company's market research analysts hypothesized that the problem lies in the timing of the commercial's message, "Drink sparkling light." Either it appears too early in the commercial before the viewer has become involved, or it appears too late after the viewer's attention has faded. After extensive experimentation, the research group finds that the percent of full attention that a viewer devotes to a commercial is a function of time since the commercial began, where the viewer's attention equals f of t, which equals -3 over 20 t squared plus 6t plus 20, when the time is between 0 and 30 seconds. So when is the best time to present the commercial's message? So we know that this is a quadratic function, and I know that because my highest exponent is a squared. So when I graph it, it's going to be a parabola. And I also know it's going to be concave downward because my a term is negative. So we're going to have a maximum. Where would that maximum occur? It's going to occur at the vertex. And if we recall, the vertex would be x, which in this case is just t for time, negative b over 2a. And I know my b value is 6, and my a value is -3/20. And -6 divided by -6/20 is the same thing as -6 times -20 over 6. And when I solve that, I get t equals 20. So I know at 20 seconds, there's going to be a maximum. If I want to find what that maximum is, I would just find f of 20. And when you do that, you end up with 80. So I know that my vertex is going to be at 2080. So if I was to graph this, I have time on my horizontal axis, and then I've got my viewer's attention on my y-axis, which is just f of t. And let's count by 2's along the horizontal. So each one of these stands for 2. So 2, 4, 6, 8, 10. And then 2, 4, 6, 8, 20. 2, 4, 6, 8, 30. And I can stop there because I'm only interested in the viewer's attention from 0 to 30 seconds. And then I'm going to count by 10s here along the y-axis. So this would be 50. And that's 100. And I can stop there. So if I graph my vertex, which is at 2080, that's going to be right there. I know that my y-intercept is 20, right? That's when time is 0. So my y-intercept is going to go right there. And then if I was to just reflect this point, I know it's 20 units away. So another 20 units would take me out to 40. But remember, I can't really go that far because I'm only interested in 0 to 30 seconds. But it would go like right about here. To get an idea. And we would sketch it here. It would look like a parabola, but again, I'm only interested in 0 to 30 seconds. So I'm going to kind of stop right there. So I can see that the viewer's maximum attention is at 20 seconds, right? Well, we can also determine this through finding the derivative. If you'll recall, from the last section, we looked at derivatives for increasing, decreasing. So I'm going to find the derivative of f of t. And if I just use my power rule, right? So if I go back to my original function, it's just going to be 2 times -3 over 20, and then take away 1 from the exponent. And then it's going to be 1 times 6, take away 1 from the exponent. So you're left with f prime of t is -3 over 10t plus 6. And I want to take that function and I want to look to see where time is greater than 0. So if I solve for this, I would get negative 3/10 t is greater than negative 6. And then I would multiply both sides by negative 10/3 so that this cancels. And anytime you multiply both sides by a negative number, remember the sign flips, and you would get 60 divided by 3, which again is 20. And we get t is less than 20. So what that means is the viewer's attention is increasing for the first 20 seconds, and then it starts to decrease for the last 10 seconds. So here you can see where it's increasing, and then here it starts to decrease. So the best time to present the commercial's message would just be at 20 seconds, right? Because the viewer is going to devote 80% of their attention to the actual commercial. All right, so here we had this point here, which was a maximum. And if you noticed, I looked at the derivative to determine the maximum of that function. So derivatives can tell us relative maxes and mins. What is a relative max and min? Well, f of x, right, our function, has a relative, or sometimes we refer to relative as local maximum at x equals some constant, we'll call it c, right? If f of c is less than, or sorry, if f of x is less than or equal to f of c for every x in some open interval around x equals c. So in other words, here's where the maximum occurs, right? F of x is less than or equal to that value right there. That value is the highest point, the highest y value. So that tells me there's a relative or local maximum. And we can say for relative mins, again, sometimes relative is referred to as local. They mean the same thing. F of x has a local or relative minimum at x equals c if f of x is less than or equal to f of c in some open interval around x equals c. So here's a minimum. Okay, and like, let's pretend here's our x-axis, here's our y-axis. This value right here is where x is equal to c, and this function is f of x, right? This value here would be f of c. So we know that there's a local minimum when f of x, these y values, are greater than f of c. F of c is the lowest point there. Okay, so think of maxes and mins as like peaks and valleys. So here we have a valley, right? For maximums, we have peaks. Okay. So a function has a relative, we call it extremum. Think of that as extreme point. Okay, the plural of extremum is extrema. So if there's more than one local max or min. Okay, at c, remember, and c is just your x value, it's a constant. If it has either a relative maximum or a relative minimum there. So if I'm given a graph, which I am here, and we need to identify the x values of all the points where the graph has relative extrema, what I'm going to do is look for my peaks and valleys. So here I have a peak, and I also have a peak right there at that sharp corner there, which we call a cusp. So peaks are where we have relative maximums. So I've got a relative max, and my relative max is f of x1, right? My maxes and my mins are my y values, and it occurs at x equals x1. I also have a relative max at f of x3, and it occurs where x equals x3. So my actual maxes and mins are always going to be the y values. Okay, now I can also see that I have a valley. So here's a valley, and here's a valley. So that tells me that I have a relative minimum at f of x2, and it occurs at x equals x2, and then f of x4, and it occurs at x4. And again, your maxes and your mins are your y values. The x value is just where that max or min occurs. Now also keep in mind that relative maxes and mins are not just singular points, they need to be in peaks and valleys. Okay, if you could pause the video and try the next problem, you want to identify the x values of all the points where the graph has relative extrema. So how do we locate relative extremum? If a function, we'll call it f, has a relative extremum at some x value c, then c is what's called a critical number or c is an endpoint of the domain. Okay, how are critical numbers related to relative extrema? So that brings us to the first derivative test, okay, which says, let c be a critical number for a function f. Okay, some things about f and c. F is continuous on the interval ab. Okay, we looked at continuity back when we were looking at limits, except possibly at c. And c is only a critical number on this open interval ab. So you're only looking at that interval. Okay. Step 1 of the first derivative test says f of c is a relative maximum of f if the derivative f prime of x is positive in the interval A to C and negative in the interval C to B. And we can see here in this diagram, we've got a relative maximum, right? When f prime of C is positive from A to C, and it's negative from C to B. You can see that there's a peak. Okay, same thing here. So what we're going to be looking at is the sign of f prime in the interval A to C, and then we're going to look at the sign of f prime in the interval of C to B. And if it goes plus minus, then that means there's a relative maximum. And the maximum will occur at C comma f of C. So the critical number, and then plugged back into the original function. You can see for a minimum, it's going to be the opposite. So from A to C, it's going to be negative for f prime, and then from C to B, it'll be positive from f prime. So it's going to go decreasing, increasing, and you can see the same thing here. Okay, so step number 2 is, or rule number 2, I should say, f of C is a relative minimum of the function f if f prime of x is negative in the interval AC and positive in the interval CB. Okay, so here's case number 1. Relative maximum means it's a positive on the first interval, negative on the second interval. Case 2 is when it's negative in the first interval and positive in the second interval. Okay, so our signs are changing. Notice that the signs change at the critical value. What happens if my signs are the same? That means that there's no relative extrema. So you can see here, you have this curve, right? There's no peak or valley. Same thing here. And then with these as well. So we're looking for sign changes. If there's no sign change, that means that there's no max or min. This is number 4. Okay. So let's apply the first derivative test to find all relative extrema for the function. Remember, extrema are just referring to maxes and mins. So we've got this function, and I want to find the relative extrema. And relative extrema are going to be y values. Okay, so that's important to keep in mind. Maxes and mins. So the first thing I'm going to do is I want to find all the critical numbers. To do that, I need to find the derivative. So I'm just going to use my power rule, and I would get 6x squared minus 6x minus 72. Okay, and we're going to take that function, set it equal to 0, and solve. So I can factor a 6 out of there. And then I know this factors into, let's see, x plus 3, and then x minus 4. So when I set each of those factors equal to 0, I get x equals negative 3 and 4. Okay, so they're my critical values. So I'm going to make my number line, plot negative 3, plot 4, pick some test points. So maybe negative 4, 0, and 5. What we're going to look at is the sign of f prime, and then that's going to tell me about f of x, whether it's increasing or decreasing, right? So if I plug in negative 4 into my derivative, negative 4 plus 3 is a negative, negative 4 minus 4 is a negative, and negative times a negative times a positive is a positive. So that tells me that f prime's positive and the function's increasing. If I plug in 0, I get a positive times a negative times a positive, which is a negative. So in that interval, from -3 to 4, my function is decreasing. And then when I plug in 5, I get all positives. So in the interval from 4 to infinity, I know that my function is increasing again. Okay, so I know that it's increasing from -infinity to -3 and from 4 to infinity. And then I know it's decreasing from -3 to 4. Okay, so when it increases and then decreases, right? Think of it as like it's going up and then it's going down. There's going to be a relative max. So I'm going to have a relative max, and I need to find that by taking the -3, the critical value, and plugging it back into f, the original function. And when you plug -3 in, you end up with 150. So I know that there's a relative max at -3, 150. The maximum is actually 150. It occurs when x equals -3, right? So 150 is the max, and it occurs at x equals -3. Okay, I know there's a relative min when it goes from negative to positive. So it's decreasing and then it's increasing. So there's a min. Okay, and the min occurs at 4. So I need to find f of 4. Okay, so I'm going to plug in 4 in again back into my original function, and f of 4 would give me -193. So the actual minimum point is -193, but it occurs at x equals 4. Okay, and we can show this on a graphing calculator. So I'm just going to pull up Desmos and type in my function, and we'll take a look at what we have here. So we've got 2x to the third, and then minus 3x squared, minus 72x, plus 15. Okay, and you can see it's a giant graph, right? So if I zoom out here, we've got this maximum point that we figured out, right? We calculated the maximum point occurred at -3, 150. So that's your relative max. And then my relative min is down here at +4, -193. So your min is, your relative min is -193, and it occurs when x equals 4. And you can also see where the function is increasing and where it's decreasing around those critical values. So the first derivative gives us a lot of information. It tells us, first of all, where these critical values are and whether the function's increasing or decreasing. And then the increasing, decreasing shows us where the function has a relative max or min, if it does. What I'd like you to do is pause the video and try the next problem, and then you can unpause when you're ready to move on. For this next example, we're going to be finding the all relative extrema for this function. Okay, my function is f of x equals 6x to the 2/3 minus 4x. So again, what I want to do first is find the derivative. So I'm going to use my power rule. 2/3 times 6 gives me 4. Take away 1, 2/3 minus 1 is -1/3. And then the derivative of -4x is just -4. Okay, so I want to set that equal to 0 to find the critical value. So I would have 4, and then we can write that as over x to the 1/3 minus 4 equals 0. I'm going to add 4 to both sides. And then I'm going to cross multiply. So just pretend this is a 1, and I would get 4x to the 1/3 equals 4. And I know I'm going to divide both sides by 4. I get x to the 1/3 equals 1. So x to the 1/3, remember, is another way of saying the cubed root of x. But you can just leave it like that. If I want to solve this, I would just cube both sides. And I get x equals 1 cubed, which is just 1. Okay, now that's not my only critical value. Remember, we need to also look at where the function's undefined, and it would be undefined here if x to the 1/3 equals 0, which of course x equals 0. So it can't be 0 or that function would be undefined. So I've got my two critical values. One of them is 0, the other one's 1. Okay, I'm going to pick some test points. So I'll plug in like -1. I'm going to choose 1/8 because I'm going to have to plug this back into here, and you can take 8 to the 1/8 to the 1/3 power, right? It's the cube root of 1/8. And then I'll plug in another number that I can take a cube root of, like 8, just to make it easy. You can use your calculator though if you want to use the table, that's completely fine. So if I plug in a negative into my derivative, the cube root of -1 is just -1. So you end up with -4 minus 4, which is negative. So that tells me that the function's decreasing from -infinity to 0. Okay, when I plug in 1/8, the cube root of 1/8 is 1/2. 4 divided by 1/2 is 8. 8 minus 4 is 4. Positive 4, my function's increasing from 0 to 1. And then if I plug in an 8, the cube root of 8 is 2. 4 divided by 2 is 2. 2 minus 4 is -2. So the function decreases there. So when it decreases and then increases, there's a relative min. So I know that the relative min is going to occur at f of 0. So if I go back to my original function, plug in 0, you get 0. So there's a relative minimum at the origin, 0, 0. And then my function increases and decreases. That's going to give me a relative max. And that would occur at f of 1. So if I go back to my original function and plug in 1, I get 2. So the y values are my max and my min, right? They occur at the x values. Let's take a look at the graph and see what we have here. So I've got 6x to the 2/3, and you'll probably have to put 2/3 in parentheses when it's an exponent. And then you've got minus 4x. So you can see here, right, that the function does decrease from -infinity to 0. And you also see that there's a relative min there, right, at 0, 0, 0. And you can see that there's a relative max at 1, 2. Okay, and notice too that there's a sharp corner where the derivative does not exist, right? We know that the derivative would not exist where x equals 0. Oh, and this should be minus 4x, sorry. Okay, again, you can see here there's a sharp corner right there where the derivative does not exist. But this is your relative max at 1, 2. And then there is a relative min at 0, 0, but a sharp corner there where the derivative doesn't exist. Okay, let's take a look at this guy. So find all relative extrema for the function f of x equals x cubed e to the x. Okay, so the first thing I have to do when I use the first derivative test is I need to find the derivative of f of x. And if you notice, it's a product, right? So that means I have to use the product rule for derivatives. So I'm just going to let u equal x to the 3rd, and v is going to be e to the x. And I know the derivative of x to the third is just 3x squared. And the derivative of e to the x is just e to the x. Okay, and then applying my product rule, remember it's u times v prime plus v times u prime. So it's just going to be x to the third times e to the x plus e to the x times 3x squared. And I have to set that equal to 0. So let's try to make life easier. We'll factor out an x squared and an e to the x. And then I would just be left with x plus 3. Okay, set that equal to 0. And e to the x is always going to be positive no matter what you put in. So I don't have to worry about that. I just have to worry about the x squared equaling 0 and x plus 3 equals 0. So here I get x equals 0 and x equals negative 3. So they're my critical values. Okay, so let's plot them on the number line and pick some test points. So maybe we'll pick like negative 4. Let's see, negative 1's an easy one to plug in, and positive 1. And plug it into the derivative and check the signs. So if I plug a negative 4 in here, I don't have to worry about the e to the x. That's always positive. Negative 4 plus 3 is negative 1. A negative 1 times a positive is going to be a negative. So my function is going to decrease from negative infinity to negative 3. If I plug in 1, 1 plus 3 is 4. Positive times positive times positive is positive. So the function's increasing from negative 3 to 0. And then if I plug in a 1, 1 plus 3 is 4. Again, the function's going to increase. So I've got two places it increases here. When the signs are the same, there is no relative extrema, right? But here I can see it switches from negative to positive. That tells me there's a relative minimum. And the relative minimum would be at f of negative 3. So if I go back to my original function, plug in a negative 3 in both of those places. So if you need to use a calculator for this, you've got in parentheses, negative 3, and then to the third, and then times e, and then it's to the negative third. And you end up with negative 1.34. Okay, and again, there's no relative max or min at x equals 0, right? Because the function does not change signs. The derivative does not change signs. Okay, if you could pause the video and try the next two problems on your own, and then you can unpause. Actually, there's another problem for you to do. So you can unpause and then pause the video again so you can read the last problem and try this application problem. And that's it for the video. Enjoy the rest of your day.